Welcome back. This is Mr. Greenstein's Geometry, and we're going to be looking at Chapter 8. We're starting with 8.1, Similar Polygons. So let's first take a look at the map of California, and then let's expand this a little bit. And notice that it looks just like the first California, but it's just a little bit bigger, so we've dilated it. And then let's dilate it some more. So you'll notice here that California has changed from this small version to this medium to this large. But the thing that is the same is that these angles inside of the state have not changed. So this angle here is the same angle as this, is the same angle as this. And if we look around the state, you'll see that all the angles are the same. So they're called congruent. If we look at the sides, though, if I take this side, you'll notice that it got longer here and longer here. In fact, it got longer in the same way that all the other sides got longer. So we call that the sides proportional. So all of the angles are going to be the same. So all the angles are congruent, and yet all of the sides are proportional, so they're bigger. So we have this whole idea of what do we call the difference between similar and congruent? Well, with congruent, all of the angles and all of the sides are congruent between the two figures. If we have similar figures, then all of the angles are congruent, but only the sides are proportional. So here I have a triangle, and I have the three angles, A, B, and C, and you'll see that they're congruent to D, E, and F. I also have the side length, so say this is side length A, and I'm going to increase that by a factor of K, so I'm going to make it as long as KA. I'm also going to take the other sides, B and C, and I'm going to multiply them times the same K factor. If I do that, then corresponding angles are congruent, and the ratio of the corresponding side lengths are going to be this K, or the scale factor. And the scale factor, if you look here at the bottom, I have KC is compared to C, KA is compared to A, KB compared to B. If I look at all of these together, you'll see that they're all equal to each other. So that equals what's called the scale factor. So we're comparing side to corresponding side of two similar figures. Now let's use similarity statement. If I say ABCD is similar, notice the tilde is for similar, to FGHE, that says that A to B to C to D is similar to F to G to H to E. What is the scale factor from ABCD to the other figure? Well, the way that we can tell that is we look for a side that is marked. And I have a side marked here, EF, which is 12. What side does it correspond with the ABCD? Well, let's look back at the statement at the beginning here, and let's find that side. So if I look for F and E, F is here and E is here. So that corresponds with A and D. I look down here and I'll see AD goes right here. If I compare the side length, 6 going to 12, that means that I'm using a factor of 2. So I'm going to multiply 6 times 2 to get 12. That means that my scaling factor, K, is equal to 2. Therefore, I'm going to take each one of these lengths and multiply by 2 so that I can show the missing side lengths for the other side. The missing side lengths I just go back to my statement up here, and I can say, well, AB corresponds to FG. So AB is 8, so FG is going to be 16. If I look for BC, BC up here corresponds to GH. So BC is 4, so GH is going to be 8. And the same thing with CD. CD is going to correspond to HE, so I'm going to make that 2 times 3, which is 6. So now I have the missing side lengths for this polygon here. List all the pairs of congruent angles. Well, A corresponds to F, B corresponds to G, C to H, D to E. And that's how we would list the pair of congruent angles. So let's talk about the theorem. There's a theorem about the perimeter of similar polygons. And if we have two polygons that are similar, then the ratio of their perimeters is equal to the ratio of any one of their sides. So here I have these two being similar, therefore they're going to be, the ratio of their perimeters is equal to the scale factor, which is their sides, any sides that I choose. So that's how we can see how the perimeters are if we want to compare. They're going to be the same thing as the scale factors of the sides. Now let's take a look at some problems. For A here, let's say that we want to figure out whether these are similar. Well, right away we can see that this is an isosceles triangle and this is isosceles. Well, that's good. That means that we can scale 10 to 5, that's just times 1/2, and 10 to 5 by 1/2. So already we're in good shape there with two sides. Now let's look at the angles. Now all the angles have to be congruent. Since this is an isosceles, then that means that the base angles are going to be congruent. Well, here I have 62, so this one must also be 62. Over here, this one is 36 degrees. If I subtract it from 180 degrees and divide by 2, I get 72 degrees for this angle and 72 for that angle. Well, you can see right away that they're not the same as that. Therefore, these don't work. These are not similar. Let's look at B. On B, I can say that C corresponds to S, D corresponds to T, A corresponds to Q, and B to R. So all of the angles of this correspond with all the angles over here. So that's one test, and that works. Now let's look at the sides. I know that DC corresponds with ST, so you can see it goes from 3.5 to 7, therefore it's a multiple of 2, multiplied by 2. If I look at C to B, that's going to be the same thing as S to R. Notice it's 3 to 6, that works. D to A is the same thing as T to Q, that's 4 to 8, that works. And finally the last side works 2 as a multiple of 2. So this one actually works, and that is these two polygons are similar to each other. Let's look at the last one, C. Here I have a equilateral triangle and equilateral triangle. Well, they're equilateral because we know that from a theorem that this is equiangular means equilateral, and this is also equiangular. So we know that each one of these is 60 degrees, and these are all 60 degrees, so that works. Let's look at the side lengths. Well, this is A for each one of these sides, and these are B for each one of these sides. Well, converting A to B, you're going to multiply by the same thing regardless of what side that you pick. So the K factor, the scale factor, is the same. Therefore, these are similar. And that's always going to be true with equilateral triangles. Now let's take a look at this problem. We have some points here. We have 0, 0, and that's A. We have 4, 0, and that's B. We have 2, 4, and that's C. And then 0, 2, and that's D. If I connect those together, you can see that I have this kind of structure. Then I have 2 points of the new quadrilateral. It's -10, -2, which is around here, so that's A prime. And then I have -2, -2, which is right around here, that's B prime. I connect those two together a little bit better. And to find the C prime and the D prime, we're just going to take a look at where the old A is, and notice that we go up 2 to get to D. Well, if A to B is 4 here, and A to B is 8 here, then we have a factor of 2, multiple. So we're just going to go from here to here 2, so we're going to go 1, 2, 3, 4, and that's where we're going to put our new C prime. And then connect that. We also have, I'm sorry, that's going to be D. So let's fix that. That's going to be D, D prime. And then to find C, we know that we go over 2, 1, 2, and then up 2. So that means we're going to go over 4 and up 4 and put a point there. And that'll become our new C prime. We connect all of these together, and there are 2 similar shapes. You can also put the points down here, and I'll leave that to you to figure out where you could put the new D prime and C prime to have congruent polygons, but down in this direction. We also have the theorem about the areas of similar polygons. If 2 polygons are similar, then their ratios of their areas is equal to the square of the ratios of the corresponding sides. So here I have 2 similar polygons, and the area of one over the area of the other, which is a ratio, is equal to the square of that K ratio. So this is a corresponding sides, and I take the square of that. So let's just take a look at what we have here. We have a polygon with the sides. Double the side lengths. Is the new figure similar? Well, obviously yes, because if you multiply by 2 times each one of these, then the new figure is going to be similar if you keep the angles the same. Compare the perimeter of the original and new figure. I'm going to let you do that. And you will find that if you compare the new figure with this figure, that you'll get exactly the scale factor of 2. And if you compare the areas, well, to get the area, we're going to have to cut this up. So we're going to have to create a little triangle here and a rectangle over here, and we add these areas up. And then take the new figure and chop that up. You will find that the area is going to be squared of what it's going to be the scale factor squared for that new area. So that's similar polygons, and we're going to be talking a little bit more about that in the next day we get together in class.